The title of my talk is 3D Modeling of Zebrafish Embryonic Tissue. I'm Lisa Manning. I'm at Princeton, and this is work in collaboration with Aggregates, who's also at Princeton University. I was going to talk to you today about surface tension and a model for that in tissues, but there's some really exciting new experimental data that makes that still more of a work in progress. And so I'll be discussing this, which is a related topic today. And so here's a few movies of motion in tissues. And so we've been told before that these embryonic tissues behave like liquids on long time scales. And the first movie is a picture in vivo, and this is nuclei staining. And so you can see that the cells are moving in this. And this is, in vivo, it's in what's called the shield of the embryo, so it's the organizer. And some cells are moving this way, but you can see that there's some motion up that way. I'll show it one more time. And so an overarching question is what drives flows in these embryonic tissues, in these liquid-like tissues. And then the second thing I'll show you is an in vitro experiment where these are aggregates of cells now, and they're moving together and fusing just like drops of liquid, basically. I think it's a really neat picture to show that this, on long time scales, this is at over 4 hours that these tissues behave like fluids. But the interesting thing is if you look at the structure, you ask the question, why are these materials behaving fluid-like on long time scales? This is a confocal image of a 2D slice through an aggregate, and blue is nuclei, and green is the membrane. And you see that the structure really does look like a foam, as we've been told before. It's a close-packed structure, and here's some 3D images. And so also you know right away that these cells are big enough that thermal temperature doesn't cause motion in these cells. And so what gives rise to this, if it were a foam like this, in order to get motion, you'd have to shear it externally. The foam wouldn't just move by itself. And there's not thermal temperature here, so how can we model these tissues? Another point is that it's not exactly a liquid. So this is a plot of the mean square displacement as a function of time window. And this is a slope 1 on a log-log plot. So you can see that at long time scales, it is diffusive. But at shorter time scales, it's subdiffusive. And in general, this is sort of an indication of caging or glassy or frustrated motion at these shorter time windows. Oh, and one other point I'd like to make is that unlike other liquids, there's no cell loss. So inside of here, these cells are behaving like liquid, but they don't ever move outside of the aggregate. And so that's also a difficult thing to model. I mean, we'd like a model to capture. And so the question I'll be talking about today is what minimal mechanical model explains and predicts these flows in the structure. And so importantly, I want to make sure that we're doing a quantitative comparison between this model and experiment as well. So I'll talk about that. And so the model that we've developed is a cell interaction model. And so we treat these cells, we talk about the cell center of mass, and they interact via a two-body potential, which I'll talk about in a minute. There's also dissipation through frictional damping. And the shape changes in this model are passive, which means that the cells change their shape based on their interactions with their neighbors. And where the active processes come in this model is through the active forcing, and I'll talk about that. And also we'll neglect inertia, so that we have an equation for the motion of each cell, which is basically the sum of a potential, a damping, and an active force. And this, for those of you who are familiar, this idea is sort of very similar to a model for foams by Doug Durian, with obviously changes. And so the interaction potential, I think, is interesting because there's other models like this, but they use something like a Morse potential. And what I'd like to point out is that what you really want is a contact mechanics model for how these cells interact. Because you're talking about macroscopic objects which are coming together and squishing. And so the area over which their adhesion acts is very small, but what's important is how much contact area they have. For their adhesive properties. And so for this model, I'll use what's called the DMT contact mechanics model. But in general, it's just, the repulsion is like elastic spheres. So these cells repel like elastic spheres. And the adhesive energy is proportional to the surface area in contact. And that's what this model does. And then also I'd like to talk about the active force. Because as a physicist, I might think that the way to model the active force would be using stochastic white noise, that inside this packing that each cell basically has some noise term that describes the active forcing. But that's not the right thing to do in this case, because this is an interesting system. There's no extracellular matrix like what we've heard about before, and these cells are swimmers. So they can't move unless they exert a force on another cell. And so that right away tells you two things, is that number one is that you have to obey Newton's third law, so if one cell pulls on the other better experience a force. And in addition, that the direction of the active force is biased, because we know that cells move by basically developing new adhesive contacts and moving in the direction of those contacts, essentially under tension. And what that means is you pull in the direction of your neighbor. You never push off, essentially. And so with that biases this active noise that you feel from your neighbors. And so that's also in this model. And so just to flash this up here, this is what the model looks like. It's basically like a position Langevin equation. And there's 3 non-dimensionalized parameters. And so what you can see is there's parameters that we can measure. And then there's 2 parameters, which is the damping and the magnitude of the active forcing, which you can't really measure, and so we'll have to try to get at that in a different way. So first I'd like to show you that, just to give you an idea of what this model looks like when you run it. And so what you see, first of all, is that you get a nice rounding up of the aggregate, and you don't get any cells exiting the packing. And that's actually hard to do, to get diffusion here in the center and not to get them to move away from the packing, and that's because of this bias in the active forcing. The colors are just to show you that they don't mean anything other than to show you that at the end of this simulation, some of the ones that were in the middle have moved up to the edges.
And why they don't move away?
Because essentially, if you had a stochastic forcing, they would, right? But because if their direction that they have to move is biased in the direction of the contacts they're making with their neighbors. Essentially, that's the idea. Also, you can worry, because some other models like this have crystallization, because you have a potential, and under agitation, the minimum energy state for these spherical objects might be a crystal, but that's not what you see. This is a pair correlation function, and for these spherically symmetric particles, if we were a crystal, you'd see peaks here and here. And actually, in some of the simulations, you see what has been shown to be signatures of jamming behavior as well. But the important point is that these things stay disordered. The other thing is we can sort of do something more quantitative, and we can look at the mean squared displacement as a function of the time window. And this is the simulation. This is experimental data. And you can see that, again, at long times you get diffusive-like behavior. At short times you get subdiffusive behavior. This red is slope 1, and this is slope 1/2, just to give you an idea. But then when you extract the diffusion constant with these simulation parameters, it's a little too small. And so what you can do is actually run a whole bunch of simulations with a lot of different parameters, and then figure out what's you can get this, you can measure what this adhesion energy is, and then you can say, okay, well, I know what the diffusion constant is in my experiment, so that gives me one of the parameters that I need for my model. So just to give you an idea that we're really trying to quantitatively match up the simulation with the experimental data. And so this is a cell interaction model for embryonic tissues that matches the experimental observations of diffusion plus subdiffusive behavior, rounding up, no crystallization. But we want this to be, we want to make predictions, because a lot of people have shown simulations, and we show that we fit the data, so this is a good, it seems to be a good model, but we'd like to make predictions. And so cell sorting experiments that were alluded to before are sort of the sensitive test of the dynamics and the timescales. And so once we do finish this fitting procedure, then we can go and make predictions about these cell sorting experiments, and that's what that's next.
Aren't the peaks and G of R still consistent with a triangular lattice instead of a square lattice?
They're not in 3D. I mean, it's, no. So do you let me go back? So these are basically, in 3D, these are signatures of tetrahedral coordination, which doesn't tile space. So, does that answer your question? Yes.
In your initial conditions, do you start the cells moving randomly, or do they move in some given direction?
So the way the simulation starts is I generate I generate a random distribution of cell centers, and then I equilibrate the cell centers without any active forcing. So I sort of let them come to an equilibrium shape, which is basically if I started them out in a cube, then they come into a cube, and then I start the active forcing once sort of the shape without the active forcing is equilibrated. And then the active forcing is just by a stochastic white noise from that equilibrated.
So they don't have an initial velocity. They just move under the forces.
They move under the forces, exactly.
You use this DMT adhesion model. Isn't there hysteresis in there, and how is it taken into account in your simulation?
That's a great question. The DMT model I'm using is the one that basically has, I'm using the force goes to zero at zero overlap. You're exactly right that in a real system there is hysteresis, because in this model, essentially once you get close, you go very quickly to the equilibrium position.
So you eliminate the hysteresis.
So I eliminate this in this model, but I agree it's very interesting and something to be looked at.
Any more questions? Thank you very much.